Hello everyone, welcome back to my channel. So today we are going to discuss another problem. So problem is counting bits. A very interesting problem. We are given an integer n and we need to return an array of length n plus 1 such that for each I means from 0 till n, all the numbers are I. So we have to return the number of ones which are in the binary representation of I. So for example, let's say n is 5. Fine. So if n is 5, we will start from 0 to 5. So 0, 1, 2, 3, 4 and 5. And we have to return an array in which like we are returning number of ones in binary representation. So in 0, if we write binary representation of 0, so that will be 0, 0, 0. So there will be no 1. So 0 only will be there. For 1, there will be one set bit, that is one in the binary representation, so 1 we will return. Over here for 2 there will be again, this will be the binary representation of 2, so there is only one set bit 1, so we will return 1. For 3 it will be something like this, so there will be two set bits, that is two ones, so we will return 2 here for 3. For 4 there will be 1 only, and for 5 there will be 5 is like this na, 0 1 0 1. So for 5 there will be 2. So output will be this 0 1 1 2 1 2. So if you see 0 1 1 2 1 2. Fine. I hope you understood the problem. So see guys, for this na, a prerequisite for this problem is Kernighan's algorithm. Kernighan's algorithm. This Kernighan's algorithm is used to find the number of set bits, that is number of ones. So this algorithm is used to find number of set bits in a binary representation. So set bits in a number. Set bits means number of ones. So how many ones? For example, if we want to find how many ones are there in the binary representation of 5. So this algorithm will give us the count of the set bits. So how many there are two set bits, right? Two ones in the binary representation of 5. So it's like this na, binary representation of 5 is like this 0 1 0 1. So there are two ones. So Kernighan's algorithm will give us the count of number of set bits. So here Kernighan algorithm will give us 2 because there are two ones. Fine. So if you are not aware how Kernighan's algorithm will work, please like go through that one. I haven't created any video on it yet, but I'll surely will make. But until then you can watch any other video and just uh, see what this Kernighan algorithm does, right? Then you can come back to this video. Okay, so see guys, one approach is very simple, right? For this problem, one approach is very simple. That what we can do is, so let me erase this. So see, let's say we are given n is equal to 5 and we have to uh, find all the set bits in from 0 to this n. So 0 to 5, for all numbers we need to find the set bits. So this will be 0 1 comma 1 comma 2 1 2. This will be the output, right? So what we can do, simply see, we can run a for loop from 0 till uh, n, right? And what we can do is, every time we just need to find the number of set bits, right? So if this is I initially will be 0, then I will be 1, then it will go till I is equal to 5. Fine. So every time we need to find the number of set bits, that is number of ones in the binary representation. So we can use Kernighan's algorithm and we can find the number of set bits, right? So for 0, this Kernighan algorithm will give us 0, so we will add 0 in the list. This is the vector final output list. So for 1 it will give us 1. For similarly for 5 it will give us 2, because there are two ones in the binary representation of 5. This is binary representation of 5. Fine. So this is one approach, right? This is basic approach which we can basically we can think of when we see the problem. So time complexity for this will be, Kernighan algorithm is log of n time, right? It's log of n time. So we are running over here this for loop from 0 to n, that is O of n. So every time for each I we will be calling the Kernighan algorithm, right? So time complexity will be O of n log n. This will be the time complexity, right? So this is one approach. See, this is basic approach which we can think of if we know how to find the number of set bits. So a prerequisite for this algorithm is you need to know what is Kernighan's algorithm. That is how we can calculate number of set bits. Fine. So yeah, this was the first approach. Now let's discuss the optimized approach. So over here in the follow-up they have written that it is very easy to come with the solution of runtime n log n, which we did, right, which is easy, which is simple basic approach. Can you do it linear time, that is O of n, so and possibly in a single pass. So we have to do it in O of n time and without using any built-in function. Fine. So let's discuss that. Let's say we have n is equal to 7. So for 7, from 0 to 7 we have to find the this all the set number of ones in the binary representation. So what will be the output? See, so for 0 we can write 0 1 2 3 4 5 6 7. So see, for 0 there are no ones, for 1 there is only 1 in the binary representation, for 2 also there is only 1, so 2 is like this na. For 3 there are two ones, this is 3, so here 2 will come. For 4 also there is only 1, so here 1 will come. For 5 there are two ones, for 6 there are two ones, and for 7 there are 7 is like this 0 1 1 1, so it is 3 ones. So this will be the output, right? This will be the output. Fine. Now how we can do this in O of n time, right? See, if you carefully notice, right, if you carefully notice, when we have let's say 18, right, we have 18. So what will be the binary representation of 18? It will be 1 0, right, 0, this will be 0. So and so see, this will be binary representation of this 18. So this is 1 2 and this 4 8, and yeah, this is 16. So 16 plus 2 18. So this is binary representation for 18, right? So this has two ones, there are two ones. Fine. Now if we see for 19, what will be for 19? 19 will be only one. See, between 18 and 19 there will be only one difference, and that will be this, because 1 is added right here, plus 1 is done. So how to add plus 1? We can just simply, this is one, this na, we can just simply change this to 1. So this will be binary representation for 19. We are just adding 1 here, right? So if this, there are two ones for this 18, for 19 there will be three ones, that is one greater than the whatever it was for 18, just one greater than that, right, plus 1. So whatever was 80 for 18, for 18 whatever was there, we just added 1 in it, because here we added 1. This rest are same, rest are same. Fine, this is clear, right? Now how we can know what is the, like, how many set bits are there in 18? So see guys, there will be in 18 na, there will be same number of set bits as there are in 18 by 2, that is half of 18. So if in 18 by 2 is 9, right, 18 by 2 is 9. So in 9 how many bits are there? In 9 we have 1 0 0 1. This is binary representation for 9, right? So there are two ones. So in 18 also there are two ones. Fine, I hope you're understanding. So this 18 is double of this 9, right? This 18 is double of this 9. So like there are as much like let's say there are x number of ones in this 9, so 18 also will have x number of ones. Fine. So what we can conclude from this? See, what we can conclude from this. So just try to understand what we are trying to do here. See, so what we can conclude here, it totally depends on whether the number is even or whether the number is odd, right? So just let me erase this. See, so see, uh, when number when number is even, when number is even, that is when we were calculating for 18, we were calculating how many number of set bits or how many number of ones are there in the binary representation of 18. Then what we did, we will find what how many set bits are there in half of this 18. 18 by 2, that is 9. So if 9 has x number of bits, 18 also will have x number of bits, set bits. Fine. But when number is odd, that is for, like we were finding out for 19. So for 19, what will be the answer? How the number of bits which are in 18, fine, which are in 18 plus 1, plus 1. So how many number of bits are there in 18? These many. That is set bits 18 by 2. So 18 by 2. Fine. So this 18, you can write like 19 by 2 here, because that, see, obviously that will give us same answer. 18 by 2 will also be 9, and 19 by 2 also will always also be 9. Fine. So what we conclude from this, is very important, guys. See, we can conclude that if number is even, let's say we are finding for I is there, we have to find some number of set bits for I. So number is even, so set bits will be whatever the set bits were for I by 2. So if I is 18, number of set bits for I by 2, which is 9. And if I is odd, then set bits will be I by 2, whatever was for I by 2 plus 1. Fine, because there is one increase, like there is one increase in the odd. So if even it is 18, then for odd is 19. So there is one difference, plus one is added in the odd number. So for that, the last bit, the leftmost bit, will be turned to 1. So that will increase one set bit. So that's why we are doing plus 1. Fine. So this is the formula. This is the main formula which we'll be using for this problem. Right, now let's dry run. I hope you understood the logic. Let's dry run, it will be more clear. So let's take n is equal to 7. Fine. So I am having a vector in which I'll store my output. So 0, 1. So I will make an array of size n plus 1, because we have to go from 0 to n, right? So here we'll have 0, 1, 2, 3, 4, 5, 6 and 7. Yeah. So here 7. Fine. Now see. First of all, for 0, see, for 0 there will be always 0 number of set bits. Fine. So 0 you can simply write that if this is L, so L of 0, simply you can write 0. Fine. Now we go to 1. So we have to find how many set bits are there in 1. So 1 is what? 1 is odd. This is our I, right? This is our I. I is odd. So set bits will be I by 2, 1 by 2 plus 1. So set bits. So this will be I 1 by 2. 1 by 2 is 0 plus 1. So this set bits is this only, this array. This is telling us, na? So L, you can represent the set bits will be L only. So L, how many set bits are there? Because this, see, why we are replacing set bits by L? Because this array is telling us the set bits only, na? Here there will be set bits, that how many set bits are there, how many ones are there in the binary representation. Fine. So L of 0, what is L of 0? 0 only. So 0 plus 1, 1. That is, in 1's binary representation there is only 1, 1. So here we'll write 1. Fine. Now let's do for I is equal to 2. Let's do for I is equal to 2. So you also try along with it. So for I is equal to 2, what will be there? I is equal to 2. This is even, right? So L of I, how many set bits will be there? L divided by I by 2. So set bits is what? This array only? L by 2. So L, what is I? I is 2. 2 by 2, which is L of 1. So L of 1 is what? 1 only. So there will be one set bit in 2. Fine. Which is correct. Now let's go ahead. So see, what we are doing is we are using these previous values. I by 2, I by 2. Right? So this is, you can say, dynamic programming we are doing. This is dynamic programming. This is the main problem and this is a sub problem. So we are using the sub problem result. Sub problem result we are using to find out the problem answer for the bigger problem. Fine. So now I is equal to 3. I is equal to 3. This is odd, means set bits will be L of I. That is how many set bits will be? L of I by 2 plus 1. Fine. Why plus 1? Because this is odd, right? So we saw that earlier, right? Why we are adding plus 1. So L, then we'll have I. I is what? 3 by 2 plus 1. So L, 3 by 2 is 1 plus 1. So here L of 1 is what? 1 plus 1, 2. So for 3 there will be 2 set bits. Fine. So see guys, we are getting correct answer as of now, right? I hope you are getting why this logic is working. See, right? So L is equal to now, now I is equal to 4. Just a second. So I is equal to 4 now. Fine. Now L of I will be what? This is even, so this will be simply L I by 2. So L I 4, 4 by 2, which is L of 2. Right, so L of 2 is what? 1. So there will be only one set bit for 4. Fine. Now see, for 5 also, for 5, I by 2, this is 5 is odd, so I by 2 plus 1 will be there. So here plus 1, plus 1. So here plus 1. So 2. For 5 there will be 2. Right. Now let's see for 6. For 6, let's see. So see, for 6, I will be 6. L of I will be, this is even, so L of I by 2. So L of I by 2, L of 6 by 2, L of 6 by 2 is 3, L of 3. So what is L of 3? L of 3 is 2. So there are 2 set bits for 6. Fine. And for 7, 7 is odd, so it will be L by 2 plus 1, plus 1, plus 1. So here plus 1. So there will be 3 set bits for 7. So see guys, this is our output array for 7. So I hope you understood the approach what we are doing. For odd, we are adding plus 1, and for even, we are using the sub problem result. So there will be same number of bits in L of I and L of I by 2 if they both are even. So if I is even, then there will be same number of bits in L of I, same number of set bits in L of I and L of I by 2. Fine. Now let's see the code for this, right? So for the first approach which we saw, n log n approach, this is a code. I will also give this code in the description. You can check this out. This is your Kernighan's algorithm, right? This function, we are running a loop from 0 to n, and every time we are finding the set bits and we are pushing it in the answer array. So this is your Kernighan's algorithm. I will also make a video on this, but like for as of now you can refer other videos. See, now this solution O of n approach. See, we are taking a vector. Fine, we are taking a vector, and initially we are pushing 0 in it. That is for this 0, for this when number is 0, then only 0 bits will be there, set bits. So we are pushing that, and then we are starting from 1. We are going to n plus 1, I plus plus, and if it is odd, if I is odd, Then what will be the set bits? It will be li by 2 plus 1, right? Li by 2 plus 1. Otherwise, if it is even, that is I is even, then it will be I by 2. And at last you can return L. Fine. So this is O of n approach. Time complexity is O of n. And space, we do not take this answer array space, so space is constant. Right. Similarly, Java solution is also same. We are taking this array and same logic. Fine. For Python, also I'll give in the description. So I hope you understood the problem and the approach. Let me know in the comments if you have any doubt. If you found the video helpful, please like it, subscribe to my channel, and I'll see you in the next video.